Thank you very much for watching this video. I would specifically like to thank the American Institute of Ultrasound and Medicine for creating this great avenue for researchers to present their abstracts, which were due to be presented at the 2020 annual AIUM convention in New York, which was unfortunately canceled, and to do this in these unprecedented and challenging times. Thank you. My name is Mike Blaivas, and I am presenting on behalf of my co-author an abstract entitled "Are Convolutional Neural Networks Trained on ImageNet Databases Wearing Rose-Colored Glasses? A quantitative comparison of ImageNet, CT, MRI, chest X-ray, and POCUS images for image quality." I do have several disclosures. I consult with these companies. However, none of them were involved in this research or had any knowledge of it. I am presenting on behalf of my co-author, Mrs. Laura Blaivas. Most deep learning applications for medical imaging analysis are developed using pre-trained neural networks, mostly because to train a neural network takes a tremendous amount of data. And once they have some basic training, almost like a very young child that can in general recognize images, they are then further trained on MRI images, chest X-ray images, CT, and now, with increasing frequency, ultrasound. Typically, the initial training and creation of the algorithm occurs on ImageNet databases, and these are databases containing a massive variety of images ranging from cats to mountains. The current number is approximately 20 million images and as many as 10 to 20,000 image classes, and these continue to grow in number. However, such color, object, and shape-rich images that appear in ImageNet databases are significantly, at least qualitatively, different from medical imaging such as ultrasound. Little is known about how such standard training images compare quantitatively to medical images, and this can be difficult to study because most comparisons are qualitative and quite subjective. We sought to quantitatively compare ImageNet database images that you've seen a collage of, used to create and train convolutional neural networks, to point-of-care ultrasound images, CT, MRI, and chest X-ray images. We created a Python-based program containing quantitative image quality assessment code known as BRISC, which stands for Blind Referenceless Image Spatial Quality Evaluator. BRISC allows for comparisons of images mathematically. The comparisons are made based on image blurring, pixel complexity and relationships, pixel variation, background variation, and distinguishing features. We randomly selected 5,500 ImageNet images, with the collage that's seen here representing just a handful of them, and compared them to 2,700 randomly selected chest X-rays, 2,300 randomly selected CT images, 1,800 randomly selected MRI images, and 18,000 randomly selected POCUS images, all of which came from de-identified public domain open access databases. Image quality results using this validated mathematical assessment range from 0 to 100, with 0 being the best image quality, while 100 is actually the worst image quality. Results were plotted graphically for comparison, and descriptive statistics were calculated for image quality of each image type. Additionally, we used a one-way ANOVA, and the standardized mean difference effect size value was calculated to compare each group to the ImageNet database quality if the differences were quite significant. ImageNet images showed the best image quality score with a mean rating of 21.7. Chest x-rays resulted in a mean image quality of 13.2, CT of 35.1, MRI of 31.6, and most interestingly, POCUS images scored the worst image quality score with a mean of 56.6. Chest x-ray image quality was rated by the BRISC algorithm as better than ImageNet image quality. The differences between ImageNet and all of the medical images were statistically significant with p-values of 0.000001 or less. POCUS image quality was statistically significantly worse than the other medical images with a p-value of 0.000001 or less. The greatest difference in image quality was between ImageNet and ultrasound images with a d-value of 2.38. The smallest difference was between ImageNet and chest x-rays with a d-value of negative 0.498. In conclusion, POCUS image quality is significantly different from ImageNet images as well as other medical image types. Chest x-rays were closest in mathematically assessed image quality to ImageNet images. This data suggests considerable implications for CNN training with medical images for various applications. It may even be more significant in the case of ultrasound images. Ultrasound deep learning developers should consider pre-training networks from scratch on ultrasound images only. They appear to be in a quality class all of their own. Training techniques utilized for CT, chest x-ray, and MRI images may not apply as well to ultrasound and might have to be adjusted. A possible solution may be designing and training a CNN from the ground up on a massive amount of ultrasound images only. This would require significant resources and coordination of efforts among many parties. Thank you so much for listening.